The topic of the talk today is an artifact in fragments that was lost on an ancient shipwreck of probably around 60 BCE off the tiny and not very heavily populated island Antikythera, which lies between Crete and the Greek mainland. This location is right in one of the principal passageways for marine commerce in antiquity between the Aegean Sea and the Western Mediterranean, and is also a place where bad weather at sea is a very common thing. So there are many shipwrecks on the sea bottom in this area. This particular shipwreck site, need to get the slide change. Yes, there we go. Was discovered accidentally by a team of Greek sponge fishers, divers who would go to the bottom of the sea, mostly off the coast of North Africa, in order to recover natural sponges. And they stopped at the island on their course in the spring of 1900, and did a dive for some reason and found that there were fragments of bronze statuary, among other things, in the sea bottom. And after their season of sponge diving, they sent a delegation to Athens to meet the Minister of Education of the government of the day and offer their services in recovering whatever artifacts were at this site, if they would be paid well for it and could have the assistance of at least one Greek naval vessel to help haul heavy objects up. So over the next 9 months or so, this is from November of 1900 through September of 1901, they were working on and off, more off than on, because the weather was usually terrible, diving to the bottom for spells of maximum 5 minutes with the diving technology of the time. This is sort of brass helmet and hose sort of diving equipment, and grabbing what they could if it was small, or tying ropes so that larger things could be hauled up. And among earlier finds were some that were regarded at the time as being quite spectacular, if frustratingly fragmentary. So to the left of the photograph that shows various sponge divers, Greek naval officers, Greek archaeologists together on the naval transport vessel Mycale. Beside that, on the left, is still very heavily encrusted bronze bust of a philosopher. It's now, with all the other finds from this site, in the National Archaeological Museum in Athens, and has undergone, underwent soon after its recovery conservation work, so that it now is not so knobbly looking. Initially, it was thought to be a boxer, I think, because of the general appearance of the still heavily patinaed piece. And we also have some other body parts of this philosopher, an arm, part of a cloak, but not the entire thing. And that's typical of the bronze statues that were recovered. The one on the right, which is a classical sculpture, was found almost complete, though in many, many fragments. This is so-called youth or ephebe of Antikythera, which has been restored several times with the missing bits filled in, and is now on public display in the museum. So among the things that were recovered during the last couple of months, when the major finds seemed to be running out, were a couple. It's hard to tell. We don't have records for exactly how many fragments were found at the time, but pieces of corroded metal, recognizably something bronzish from the color of the patina, which were not recognized as being anything in particular, but were stored in the museum in a place where various unidentified pieces of bronze were being kept, in the hope that sooner or later they might be fitted into the youth statue or one of the others. And they lay there until several months later, the same Minister of Education who had negotiated the deal with the divers, now out of office, paid a weekend visit to the museum, was shown this room, and noticed a couple of these lumps as having on their surfaces visible mechanical features You can see from these photographs from the time before any conservation work had been done, the larger fragments shown front and back on the bottom of the part of the slide, you can see some of the larger gears are visible here. And also, there could be seen tiny Greek lettering in inscribed texts partly in mirror writing, because these were actually not the original inscribed surfaces, but layers of patina material that had caught the impress of mostly lost bits of inscribed plate. So the combination of inscribed text, most of which was utterly illegible at the time, and mechanical features, most of which, well, and all of which were completely inexplicable in their original function, made this a very intriguing object. The discovery was extensively covered in the newspapers in Greece at the time. There was only one foreign news story reporting it that I've been able to find in the London Standard. I'm showing it on this slide. You can see how brief it is, and it simply says that there had been a discovery in the museum at Athens of an astronomical instrument which appears to have been used as an astrolabe. That was one of the earlier speculations about it, that it might have been an astrolabe, which it definitely was not. But the astronomical instrument, this was coming from some of the very few letters that had been successfully read within those first days, which turned out to be the Greek word for the sun, helios, and the beginning of the Greek name for the planet Venus, or the goddess Aphrodite. Aphro was visible, but in the context, it seemed likely that it was in fact the planet's name that was there. And that was pretty well all to go on for saying it's astronomical, but it was in fact a correct identification, general though it was. So real advances start in the 1950s with Derek de Solla Price, who was a British, then American historian of science and a specialist in the history of gearwork devices, a history that was generally regarded as beginning in the later Middle Ages with the European astronomical clocks. But Price was interested in tracing earlier, and he found in the not particularly abundant older published literature on these fragments in the Athens Museum in the early 1950s, and by the late 1950s had managed to get a modest grant to spend about 10 days in the museum studying the fragments in person. They were not at this time on public display. They had been in a display case in the earlier 20th century, but after from the time of the Second World War, when everything was put in safe storage, they were just being kept in cigar boxes in the museum's basement at that time. You can actually see, while Price is examining the largest fragment, the so-called fragment A, in the trays in front of him, you can see other fragments, including one cigar box that has just little crumbly bits of corroded metal, which he was able to take a sample of to do have some chemical analysis, which was not particularly revealing about the content, except that it appeared to be a low tin bronze. But Price was really he attempted to try to figure out with more precision what this thing was, not getting terribly far in his first spell of work on it in the late 50s, but he could see that it was clearly very complex, something utterly unprecedented for any pre-medieval period. We now know that in that largest fragment, there are 27 gears, either entirely or mostly incompletely preserved there. And in other fragments, 3 other fragments have 1 gear each in them, so a total of about 30. He couldn't see them all at that time, but he recognized certain key things. One, that most of the parts were in their original configuration; they had not got moved around under the sea. He recognized the importance of careful measurements, counting of the teeth on the gears, and getting as good a reading of the inscribed text as possible, all as routes to being able to get a better understanding of the original purpose. He had a collaborator, George Stamiris, who was an epigrapher who read as much as he could of the text for Price, who was not a classically trained scholar. So there were limits to his ability to work with that material. But in fact, the transcriptions were there was more noise than signal still in them. The level of corrosion, the tininess of the letters, the fragmentary character of what was visible were serious obstacles to getting very much out of it. But a little more terminology was there. Nothing like whole sentences or even phrases. Then in the early 1970s, something that Price had earlier hoped might be possible did become possible, and that was radiography. By then, it was possible for, with the collaboration of a Greek physicist named Karakalos, to have radiographs made of the major fragments using a portable X-ray device. And with the aid of these, Price was able to see better the configuration of gears in the interior of fragment A and other concealed features of the fragments, things that were covered under layers of other material that had got stuck on top. These radiographs, of course, were simply two-dimensional images of what was a very complex interior. I think I have a radiograph to show you. No, I don't. I'll show you radiography later. But what was a very complex three-dimensional structure of layered gears. There was really no clue from the radiographs that could say which elements were above or below other elements. So the work that Price did in its details mostly has turned out to be incorrect. Some parts are borne out, but more than say 2/3 of his attempted reconstruction of how things connected has turned out not to be right. But essentially the program of study was prophetic for the huge stages of progress that happened since then. The first being the work of Alan Bromley, an Australian historian of computers, and Michael Wright, a curator from the London Science Museum, who spent several periods around 1990 in the museum doing very careful direct observation of the fragments, as well as more radiography of higher quality than Karakalos had been able to do, and including some that was done with the little apparatus that Wright made that I've shown in the bottom photograph is what's called a linear tomography device. It has a slider that moves the photographic plate and the X-ray source simultaneously while the radiograph is being made in such a way that one geometric layer of the object that is being radiographed will be in sharpest focus, and the further above and below you get, the blurrier it gets, so that you get a kind of analog representation of the three-dimensional structure if you make enough of these. And Bromley died not long after these visits and didn't really contribute very much to the successful analysis of this material, but Wright wrote a series of wonderful papers in the 2000s, mostly between 2000 and 2006, that were really insightful about elements that Price had either not been able to explain or had come up with incorrect explanations for. And so a large part of our present understanding of the mechanism is Wright's work. Following that, in 2005, there was a collaborative project called the Antikythera Mechanism Research Project, which was a collaboration of academics, mostly scientists, some classicists, museum people, and tech people from two companies. One of them was a British company making very high power, high resolution X-ray tomography devices. And we're now talking about computed tomography. The same principle as medical tomography, but higher power for purposes like looking at stress on turbines and things like that. And their best machine of the time was just small enough to be able to get into the museum's basement, as you can see in the photograph at the bottom. And they did tomographic imaging of all at what that time had become 82 identified fragments, many of them very, very tiny flakes of plate, some maybe with a letter or two of Greek on them, but also the major fragments. And the other tech group that came was a team from Hewlett-Packard, now disbanded, alas, that had developed what's now known as reflectance transformation imaging, a kind of digital processing of digital photographs that makes files that simulate looking at the photographed surface with transformations of its reflectance properties and with simulated illumination from whatever direction you like. Very powerful technique for objects in which it's the surface shape that you're particularly interested in, like heavily weathered inscriptions, or other things where you're not particularly interested in the information coming from the surface coloration. So just in quick view, here are the 82 identified fragments, a few of which I'm a bit dubious about whether they really belong. We're not really clear at what time they were found in the museum's basement between the 1970s and now, and why they were grouped with the identified fragments, but most of them are clearly authentic and belong to the device. And if you've never been to the museum and seen the fragments on display, they all are now on display. They are astonishingly small. Even the biggest fragment is only about 13 or so centimeters broad, maybe a little more, about 15 maybe. So this is very miniaturized technology. And the inscriptions are very tiny too, the ones that you can see. I'm just going to show a movie made from the X-ray tomography of fragment A, the one that has the most of the mechanical parts, including the 27 gears. Essentially what we're doing is like an elevator ride front to back through this fragment, so that within seconds you will see coming and going all these different details. And that's it. So you can see how powerful the tomography is for getting the three-dimensional structure. I mean, Wright had got a long way towards getting everything correct with this, but the tomography did make it possible to fit in the last few uncertain points of that. The other thing that the tomography was able to do for us, I mean, I wasn't part of the original team, but I joined the collaboration later. That wasn't really anticipated was that it turned out to be hugely valuable also for reading the inscribed texts, as much and even more than the reflectance transformation imaging, because partly because of clarity, but also because there are many parts of the inscribed surfaces that are embedded within the fragments, or that are covered with layers of patina, so you cannot actually see them or photograph them. You have to use X-ray tomography to bring them out. So here's a schematic diagram that shows essentially the part of the mechanical reconstruction that we are about, let's say, something like 97% sure of all details for. There are some aspects of this sort of module of gears that are not certain because they're close to where the gear work comes to an output in the form of a pointer revolving around a dial, and we're missing that little bit, and there may be some bit of how the connection worked that we can't restore. But most of these are extant gears, even if only fragmentarily. There are only 3 or 4 of them that have to be conjectured entirely, and those conjectures are, for the most part, absolutely solid. And the reason we can be sure of that is not only from the physical evidence of where they are and what they are now, but also from the astronomical functions they serve, which are often guaranteed by our ability now to read the texts. And I mean, to start with, around any dial that is preserved in part on what were the dial faces of this device, the dials had scales that interpreted what a moving pointer was showing. So if you have a dial that has, for example, a division of a circle into 360 degrees divided into sectors labeled with the Greek names for Aries, Taurus, Gemini, and so on, then you know that's a zodiac scale. It's showing an output or outputs that are positions of heavenly bodies as they pass in their various periodicities through the zodiac. Or you have one that has a division into what are clearly identified as months of a calendar. Well, that must be a calendar output, and the gear work must be such that it will produce that output. So we are at a very, very good level of confidence for what I'm showing you now. And now I'm going to just take us into a kind of speculation of how a program of developing such a device might have set out. At the same time, in so doing, I'll also be telling you what we know that this thing was really doing. So we're starting off with things that were pretty fundamental to what Greek astronomy was about in the period leading up to when the shipwreck happened, even after, so around the middle of the 1st century BCE. One of these is astronomy as a framework for controlling calendars. There were Greek cities, for the most part, each had distinct calendars with distinct month names, distinct decisions for when the year began, distinct things you did through the year, like different religious festivals, and other sorts of rules of operation. They all were lunisolar calendars, so they are using the phases of the moon as the basis for dividing time into months. So these are months that can be 29 days or 30 days long. And then the years need to be kept in the long term in line with the natural seasons. So these lunisolar years will sometimes have 12 lunar months, sometimes 13 lunar months. And so astronomy gave bases for being able to move from a sort of observational and somewhat capricious way of maintaining these alignments of the months and years with the desired phenomena to a regulated one that becomes more rule-based. So you don't really need to be observing phases of the moon anymore, or observing, say, summer solstices, to be able to keep your calendar in good synchronization with the phenomena that it should be synchronizing with. So this is very important culturally. Calendars are the framework for religious life, for civic government, commercial life, and they are driven by time units that are essentially astronomical time units, days starting with sunset or sunrise, months synchronized with the moon's phases, though they were sometimes allowed to get out of phase temporarily for various civil agendas, but they would have to get back into line at some point. And then years that were supposed to be in some way tied to phenomena like when certain bright stars or constellations become visible, or solstices or equinoxes. So if you're going to try to turn this into a rule-based thing, cycles are the way to go. And by the late 5th century BC, we know that some Greek people active in astronomy, in particular a fellow in Athens named Metone, were aware of a period relation which was already known in Babylonia and was independently found in China, which equates 19 solar years with 235 lunar months. And this is a very, very good equation. If you use it to run a calendar, and essentially you use the moon as the observable regulation, you're just simply starting months with new moon crescents, say, your years are not going to drift off the seasons perceptibly for centuries. You can assign a number of days to this. 6940 is the nearest whole number. Then you can turn this into a calendar structure by saying, basically take those 235 months and partition them into 12-month years and 7 13-month years. And you can even assign each month in that cycle with a month length, 29 or 30 days. And it's nice to notice, by the way, that the number of 29-day months and the number of 30-day months are both divisible by 5, which is just accidental, but rather nice for a reason I'll come to in a second. And then if you want to make this also consistent with a 365.25 day year, you really need to multiply the cycle by 4 to get a 76-year cycle, and take 1 day off the total somewhere in the cycle. And then you get something that will essentially tie days, months, and years really well for long periods. So that's one thing that a designer of an astronomical gearwork mechanism might want to do, to make a device in which basically you have some kind of a drive, maybe hand-driven, that's going to put gears in motion, and there's going to be an output that shows essentially the calendar structure in simulated time. I mean, the idea for a device like this is that your mechanical drive of time is way faster than real time, so that you can show things computed effectively over decades at a time in a matter of a few minutes of operation. So a second framework, again, very cultural rather than astronomic, which is one that ties Greek communities together while the calendars are much more local, is the cycle of the religious festivals that were associated with mostly athletic competitions, like the Olympic Games, for example, held at Olympia every 4 years. And there were others. On the slide, I'm listing the 4 most prestigious ones that attracted visitors and athletes from throughout the Greek-speaking world. Cities had, many cities had their local versions of these Panhellenic games as well, which had less cachet to them, often more local interest, but they had ambitions to being comparable to games like the Olympics. And then a third one, more about the natural world and the agricultural life and sailing, things like that. Are phenomena that are tied to the natural seasons more tightly than a lunar calendar can be. Solstices and equinoxes, by the time we're getting to, for our mechanism, the division of the zodiac belt into the 12 equal zodiacal signs, and then the sun is passing in various counts of days that are average around 30-ish through each of these signs. Appearances and disappearances of stars and constellations through the year, patterns of weather in any particular locality that seem to be seasonally repeating, life cycles of plants and animals. Physicians would be noting patterns of community health, agricultural activities, and is this a safe season for commercial sailing? All these kinds of things. Really what you need is a kind of solar year structure to be able to coordinate them, and a lunar calendar is not a good framework for doing it. So that is another thing that our mechanism may want to be simultaneously showing as an output. So you want a lunar calendar output, a 4-year cycle output for the Panhellenic Games, and a solar year output for all these natural phenomena and social things like agriculture tied to that. So our first task is to design this set of simultaneous outputs driven by one driving input. So we can suppose then, because that's what we actually got in terms of the mechanism as we now know it was, is that you're going to have a front face on this box-like device that shows the solar year material. And so it will have a dial that will show the movement of the sun through the zodiac, and a way of coordinating that with the other astronomical facts that are tied to the solar year, which are the cycle of the sun entering signs of the zodiac and the stars appearing and disappearing. On the back face, you're going to have dials for the more social time structures, calendar, and the game's 4-year cycle. So how do you want that? Well, this is, I'm basically showing you a pared down version of how we now understand the mechanism of it as having looked, with these elements showing. So this is what we call the front face, with just a dial for the sun at the moment. And the sun has a revolving pointer with a little golden ball on it. And you're going to drive this thing with the side knob clockwise. About 4.5 turns is going to make the sun pointer go once round for a year's motion. So that's showing the sun in its movement through the zodiac. And then to get the stars into the picture, there's not room on a dial scale to write all these little names of constellations appearing and disappearing. So instead, the device uses a kind of, I've shown you these, it uses a longer inscribed text, which is a list of these phenomena indexed by letters of the Greek alphabet. And these same letters appear around the dial in much more tiny form. There are enough of these phenomena listed that it has to go around the alphabet just a little under twice fully around the alphabet. So alpha through omega for 1/2, and then alpha through sigma for the other half. And so the index will tell you when the sun pointer is pointing at one of these little letters on the scale, it will tell you what corresponds in terms of star phenomena or the sun entering a sign. like something like, for example, the constellation of the Lyre. Our Lyra sets in the morning. Essentially that's what was actually inscribed there. Things like weather were not inscribed, but you might have some separate key to connect with that. So how about the material that we want to put on the back face? I'm showing you here fragment A, so you can see where the side input drive is coming in. That's the crown gear that is now labeled as A1. It's a 48 tooth crown gear, so its teeth are running sideways and engaging with the, we think, 223 teeth of the big cross-spoke gear that is the sort of visually dominant feature of this fragment as it is preserved now. And that is a gear that will revolve once fully round for every simulated solar year. So this can drive the output on the front directly. There are no further gear connections needed to get the front dial display of the sun's movement. So the back, here's a dial that's going to give the calendar structure. Why is it done in this funny way? It's a spiral slot with a scale of little cells running around that slot 5 times round. Well, if you count the cells, now we don't have them all, we have about 1/3 of them preserved, but you can easily extrapolate and you find that there are 235 cells. And so this is obviously, and Michael Wright realized this is obviously a representation of that 19-year, 235 lunar month cycle. And it's being spread out over 5 turns, because if you're going to want to have labels giving month names and year numbers in a cycle for 235 months, you can't do that in one scale running once around. It would just be too granular, too tiny. So the designer has opted for 5 runs through this round are going to give you the full 19-year cycle. And notice that number 5, this very conveniently gets in the divisibility by 5 of the numbers of 29 and 30-day months. So this little inset shows a blown up in size, a translation of the dial scale inscriptions. There are Greek words like Eukleos, Artemisios, Pseudrius, and so on. These are names of the months of a calendar, which we believe was the calendar of ancient Corinth, and was definitely the calendar in fairly widespread use in Northwest Greece during the Hellenistic period, the last centuries BCE. So we can sort of localize the area of interest for the particular calendar inscribed on here. And effectively this dial, if you simply read along the whole spiral, you are getting the entire 19-year structure, with some of the months sometimes repeated twice when you have a 13-month year. And we know from the one surviving instance that the doubled month was one that was named Macanius. And inset, there's a little dial that survives that is inscribed in Greek, of course. I'm showing it in translation, with labels saying year 1, 2, 3, 4, and outside that, names of Pan-Hellenic games. And the inscribed names include the 4 prestigious ones, the Olympics and the others, as well as 2 more local interest ones, the Haliea, which was a set of games that were held on the island of Rhodes, and the Na, which was a festival held at Dodona in Northwest Greece. So again, associating with Northwest Greece as an area of interest for the inscriptions, except for the Rhodes reference. And I'm just shading spokes of the dial. They're not actually shaded on the object, but the point of this is to bring out the divisibility by 5 point, that you can basically say, and the inscriptions did this, that any month that is in one of the grayed out spokes is going to be a 29-day month. So you have to deduct 1 day from that month, and all the others are going to be 30-day months, except that every 76 years, you have to pull out 1 extra day from some 1 month of the cycle. And as a guide to that, we believe there was another inset dial, the one that's labeled with the Greek letters alpha, beta, gamma, delta on it, that had a pointer going once around every 76 simulated years. So you have a pointer going 5 times around every 19 years, one going one time around every 4 years and one going one time around every 76 years. It gives you all this sort of calendar-based information. And the pointer had to be rather fancy in structure because it had a little pin that rode along the slot, and that was meant to indicate so that you could see which of the turns of the spiral is the one that's current, so that it has to vary in radius. So it's not fixed mount on the axis, but instead is riding freely within a pair of washers. So just labeling these dials. And how about the gear work? Well, it would be very easy to do the conversion from solar years to the Metonic 19-year cycle spiral dial output, and the others are pretty easy to get from that. You just need 2 gears to do this, very simple. And these are gears that would have been quite practical in scale for the mechanism. What actually is used is something more complicated. Why? Well, it's because some of these gears are being used for more than one purpose. We're going for a multi-output device. I'm so far only talking about 4 of these outputs, but there are more coming. And they all ultimately branch out from the starting point where we have the crown gear driving the big solar year wheel. But at some various points, you're going to have 2 series of engaged gears branching out from a single rotating axis. And so if you can get a group of gears that will function for 2 outputs up to a certain point, then that can give an advantage to using a more complicated set of series of gears for a particular output. So here we have these 53-tooth gears, for example, which are actually canceling out in their function for this particular output, because of essentially one is in the driving position, the other in the driven position. And so the effect of the number 53 for the teeth is simply nullified by this. And it's a funny number to choose, but it turns out to be important for one of the other outputs where it doesn't get canceled out at a key moment. All right, so we're on to a further agenda now. We have the sun being indicated on the front as going around the zodiac with its little gold ball and a pointer. We have calendar stuff that's relating to lunar months. How about showing the moon on the front too? So it's going to be going around the zodiac much faster than the sun, and it will need a pointer as well, driven by a different series of gears. So again, this Metonic relation, the one that is used for the calendar structure, this also gives what you need to get the moon's movement in longitude, as we call it. Its revolution around the zodiac. Basically, since lunar months are like a difference between lunar motion and solar motion through the zodiac, adding together the 2 numbers, 19 and 235, gives you the number of full revolutions of the zodiac that the moon does in those 19 years. So again, we have a ratio 19 to 254 that our gears need to do. And again, this is a rather complicated series of gears here. This is the one series that Derek Price basically got right almost completely. It's not quite the most efficient one, but it does fine. The main issue with this particular output, and it's simply inherent in what the mechanism is being made to do, is that it's a major speeding up from a drive that's going basically once around to a drive that's going more than 12 times around in the same amount of input motion. And that is mechanically risky. It's inviting jamming of the mechanism. You have to make sure that your parts engage very well so that you're not going to get jamming on a regular basis. And even at that, you probably have to open the thing up from once in a while just to get the gears back in good mobile order. I just want to point out near the end of this series, where you have 2 gears on the same axis that are both with 32 teeth, I've marked a little kind of break between them. That's because there's an intervening bit that I'm going to come to presently that complicates the motion. But if you didn't have that, if these simply connected through tooth engagements or shared arbors, as they're called, then we would simply have a gearing up in a ratio of 254 to 19, which is just what is wanted to get at least the average motion of the moon through the zodiac in correct ratio to the sun's. Well, we've got a pointer for the moon. Wouldn't we love also to have a display of the moon's phases, maybe visually in this case? So a little ball showing through a circular window that is going to be revolving with the right rate for the moon's phases. Well, we've already got the moon's phases sort of built into the lunar calendar on the back. But it would be hard to tie that mechanically to an output on the front in this position. So instead, what's going to happen is really using that fact that this is a difference of motion. We have a part moving with the rate of the moon through the stars, a part moving with the rate of the sun through the stars. So if we can find a mechanical way of doing a subtraction of rates of motion, then maybe we can turn this little ball. And this was done. This is essentially, the first known differential gear work, using a crown gear that is mounted on the part that revolves with the moon's speed and is engaging with the part that moves with the sun's speed, so that you get the difference of motion transferred to the little moon ball. And we have a good deal of this actually surviving. It's visible on the backside of the fragment we call C. We're seeing it from the inside side of the mechanism. The ball itself is lost, but you can see the little circular orifice where it must have been showing through. And you can see, though it's hard to make out what it is without tomography, the shaft that connects it to the crown gear that drives it. So this thing that looks sort of like a jar cap is actually a case that would have had the moon pointer attached physically to it on the outside. That is entirely lost, and had the little moon ball showing through a hole in it. This was a part that Price simply could not account for. He thought maybe it was part of the drive crank on the side. He didn't get the right interpretation for it. It was Michael Wright who got this. All right, we now have the sun and the moon moving around the zodiac. By 60-ish BCE, it is well established in Greek astronomy, and really has been for some time, that these two motions are not uniform as an angular rate of motion observed from the Earth. In the case of the sun, one way that you would detect this is if you can find from careful observations of solstices and equinoxes that the time intervals between consecutive solstices and equinoxes are not all equal quarters of a solar year, but have a bit of variation from that value. And for the moon, this is less obvious, so it's a bigger variation. But this is something that had been well known as a phenomenon in Babylonian astronomy since easily the 4th century BCE, or actually probably earlier than that, and was a well-known thing in Greek astronomy already before 300 BCE. So if we want to get this into the mechanism, how are we going to do that? Because all the techniques of using gears up to now have been essentially converting one motion. If you consider that motion to be uniform, then all the outputs driven by it will be uniform too. I mean, a hand-driven thing obviously is not going to be really uniform, but I mean, if you think of one round as being representing a constant rate of turning, then all the outputs will be equivalently coordinated at a constant rate. So for the sun, it seems, I mean, this is one of these things where interpreting the physical evidence has led to some disagreement, but I'm endorse an interpretation of what's seen that was put forward by James Evans and Christian Karman a few years back, which is that the variation in the rate of the sun's going around is not mechanically generated in the mechanism. It is generated by having the scale on which the output is shown having a non-uniform division. So what we can actually measure on the surviving bits of the scale is that the spacing of the degree marks on the zodiac scale is not essentially 1 degree mark to 1 degree of arc as a measured angle. How you get that out of measurements is really quite tricky, by the way, but is a little bit smaller than that. So which suggests that parts of the zodiac scale are more tightly spaced and parts are more broadly spaced in a way that effectively makes the sun pointer sweep out physically equal angles and equal times, but in terms of the read-off, unequal angles and equal times. And the way that a spectator could see this is through a second scale, and we do have part of this, that is representing effectively days of a solar year, and this one being uniformly divided into 365 divisions. This, the one calendar known to the Greeks in antiquity that used a 365-day year is the Egyptian calendar. And it had no leap days at this time. Before Roman rule came in, the Romans said, you have to have leap years, you have to have leap days. The Egyptians had a 365-day year that gradually shifted relative to the seasons by 1 day every 4 years. And so on the mechanism, this scale has been designed, so it's actually was removable and could be installed in different orientations relative to the zodiac dial, according to what was the match for a particular range of dates you're interested in showing. That's why they're sort of clip-like things that I'm showing on this drawing. So for the moon, it's different. This was done mechanically and in a way that is quite ingenious. So one of the current ways of theorizing the moon's variable apparent speed through the zodiac is to hypothesize that it's moving on a circular path, a circular orbit that has the Earth in its midst. So we're seeing the moon orbiting the Earth through the zodiac belt, but the Earth is a bit off center, or you could say the orbit is a bit off center. And it should say circular orbit, sorry, that's a typo. The average speed is about 13 degrees, 11 minutes per day. But because it's off center, you're going to get an appearance of variable speed. When the moon is near its apogee, then it will appear to move most slowly. What complicates matters for the moon is that the line to the apogee is itself slowly shifting forward by about 7 minutes per day. And this is something that was measurable and one had a reasonably good measure for. So then how to mechanize all this, a variable speed and a variable speed that is changing the directions to maximum spot, minimum spot. Well, to get to that turns out to go by way of a different task entirely, which is eclipse prediction. So basically, we're moving into something that's involving the sun and the moon in yet a different way, where you get the lineup of Earth, moon, and sun, so that the moon's shadow falls on the Earth, and you get a solar eclipse visible in some place, or the Earth's shadow falls on the moon, and you get a lunar eclipse shown in a certain, well, visible wherever it's night. So one way one might want a mechanical device to simulate this is to actually simulate the three-dimensional geometry that makes eclipses possible in some months and not in others. That would be a pretty tall order. The other way is to treat eclipses essentially as a periodic phenomenon and to indicate when eclipses can or cannot happen through some kind of a dial display without actually showing the eclipse in a visual manner. That's the route that the designer of the mechanism took. And to do this, another of these basic ancient cycles was employed, one that doesn't directly involve the sun, but that essentially a count of lunar months that brings about repetitions of lunar eclipses pretty well. In other words, it brings the moon back to a configuration with Earth and sun in 3 dimensions that is pretty close to the starting configuration. And this involves essentially getting close to a whole number of different cycles relating to the moon. It's speeding up and slowing down. It's north and south wobble around the path of the sun through the zodiac, and the lunar months themselves, because of course solar eclipses only happen at conjunction of sun and moon, lunar eclipses only at full moon. So you have these 3 different things that need to be correlated in some cycle as well as possible. And by chance, nature has given us this just short of 18-year, 223-month so-called Saros cycle that it does it fairly well. It's not as good as the 19-year calendar cycle. And it's on the basis of this that the designer chose to get a lunar eclipse display on the other half of the back face of the device. So another spiral dial, this time divided in 4 turns and divided into 223 cells. So any cell represents a lunar month in the cycle. If it's a cell in which a lunar eclipse could happen, not necessarily visible in a particular place, then it's going to have a tiny little coded text saying lunar eclipse possible. If it does happen, this is the time of night that it should be at mid-eclipse. Or if it's a month that could have a solar eclipse in it, similarly, we'll have a little coded thing saying this is a possible solar eclipse month, and this is the time approximately when, of the day in this case, when you might see the mid-eclipse. These predictions, by the way, are not hyper sophisticated eclipse theory, and that's also interesting for giving us a bit of a sense of where Greek eclipse theory was around this period before it's reached its culmination about 200 years later with Ptolemy. Again, basically driving that kind of thing is again a matter of finding a series of gears that is going to do the job. And that series of gears, interestingly, must have a gear with some multiple of 19 teeth in it. It doesn't have to be 19, it could be 2 times or 3 times. And it has to have a gear with 223 teeth. And that's because these are both prime numbers in the ratio that you're trying to get. This is basically a drive going from the input through to this eclipse output. And so they're going to have to be one rather big gear to have 223 teeth on it. So I'm showing you essentially what was used to do this, or rather a simplified version of it, because what's actually done is more complicated again. And you'll notice again, those 53 teeth gears are showing up in this train towards the beginning and towards the end. This series is actually sharing gears with the earlier one I showed that I said was more complicated than it had to be because there would be some efficiency from having gear trains branch out. And again, the 253 gears are canceling out for the output, but they are not canceled out at the stage where the 223 tooth big gear is being turned. And that is for the reason, these are the shared gears, the reason that with this series up to that gear, that big gear is now going to turn with a period which is in simulated time, the period of the apogee of the moon's orbit going around the Earth. So we now have a platform that is like a picture of the moon's slowly advancing orbit, its eccentric orbit, and we can use it to mount something is going to give the variable speed element. And we luckily have the gears, only half of them preserved, but that's enough, that do it. This is the big 223 tooth platform. And here in this inset are these half gears. You can see 2 of them, but behind each of those, there's a second gear. In the upper case, the gear that you see has another gear below it that is identically mounted, though on an independent axle, an independent arbor. So one is sort of concentric with the other. The lower pair, the gear underneath, is a little bit off center from the one above. And this is the key to the non-uniform motion. There's a little slot in the gear here. And in that slot, though a photograph really doesn't catch it, there's a tiny pin that is fixed on the hidden gear, the one lying behind that's a bit off center. So that as the visible gear is turned by the mechanism, this is the one that is directly connects with the input, it will use this slot and pin to turn the hidden gear, but in a way that speeds up and slows down because of its off-center arrangement. So this is kind of schematic drawing. And in the lower right, I've sort of blown up the structure of this to show how the pin on one gear and the slot on the other gear are producing this effect of speeding up and slowing down. And all of this riding with a gear that's moving with the moon's apogee so that you get an output which is speeding up and slowing down rather subtly. It would be something of a challenge for an operator to convince a viewer that this is really changing speed, but there are ways you could do it. So I'm now going to come to my last task, and this is one where we're more in a field of uncertainty about how it was done, because we're now moving into a part of the ancient mechanism that we have to conjecture. We have we essentially have almost nothing of mechanical remains relating to it, and So we become very dependent on the inscribed texts for knowing anything about it at all. And that is to bring in the other heavenly bodies that are known to Greek astronomy besides the stars, sun, and moon. And that's the 5 planets visible to the naked eye: Mercury, Venus, Mars, Jupiter, and Saturn. So why do we think that the designer incorporated this in? There were reasons lying around already before the more recent imaging work was done, that already had at least some people, like Michael Wright, convinced that there must have been planetary gear work that is simply not part of what was recovered by the sponge divers. One is that there are ancient texts in Greek and Latin literature. I mean, particularly valuable are passages in the Roman statesman Cicero's philosophical dialogues that talk about devices that mechanically simulated the movement of the 7 heavenly bodies, sun, moon, and 5 planets, and that, as Cicero speaks of them, had with a single driving motion, were driving the disparate rates of movement of these 7 distinct visible bodies. And in one of these passages, he also refers to displaying eclipses in some way as being part of the function of one of these things. Secondly, we have that reference that was read within the first days of the discovery of the fragments, the naming of the planet Venus. So this is something that was part of the original recognition that this was an astronomical device, but was not, nobody had actually found out how Venus fits in. And then there are various sort of physical things, mostly on that big cross-spoke gear that were unexplained. And there's one gear that's unaccounted for that's in a separate fragment, a 63-tooth gear that isn't connected now to anything, and we had no evident functioning in relation to the sun, moon, calendar stuff. But now we have texts that talk about it, and these are the same texts that were partly legible before, but now we can read almost 100%. One of them was on a plate that used to be stuck on the back side of the fragments, and that we now can see was a kind of inventory of all the exterior features, like all the dials, the pointers, and so on. It's like describing what you see when you see the mechanism. And it has a part that is talking about some system of moving parts. Pointers with balls seems to be the probable way to go with that are on the front face, along with the sun pointer with its golden ball and the moon phase ball and pointer. And they're listed in what is the standard Greek order for planets from the nearest to the Earth to the furthest to the Earth. So the moon comes first, then Mercury, Venus, Sun, Mars, Jupiter, Saturn, and then stars. And then another very difficult to read inscribed plate, which was stuck on the front, is again describing movements of planets in their cycles. So these are the periods in which the planets that seem to be are observed from the Earth to be moving around the zodiac, but sometimes approaching the sun, sometimes receding from the sun, and sometimes going in the forwards eastern direction, and sometimes reversing to a retrograde western direction. Intervals of days in which they do each stage of these things. So these texts are describing basically astronomical statements about the motions of the planets, which only make sense on a component of the package if there was some kind of an integration of these things into the mechanical displays. So I'm going to skip over this, but this is basically the ancient types of theories of circular motion that could produce these sorts of alternations of forward and backward motion for planets. And gears would lend themselves well to this sort of thing if you can get the varying speed and reversals of direction to do that. And of course, we've seen how that's done for the moon. So similar kinds of pin and slot arrangements could have done this for planets as well, not just varying the apparent speed, but getting the back and forth movement correctly to be done. And there have been several proposals for how one might conjecture gear work to do this, but we do not have enough facts to go on to be able to evaluate any particular hypothesis for this. I'm just going to close with the kind of cosmological picture that I think would have been shown on this dial, because it has these pointers with little balls on them, probably in appropriate colors for the planets. And so you would get a kind of mobile representation of the common sort of Greek, like a slice of an onion, sort of layers for each of the moving heavenly bodies going outward from the Earth at the center out to the stars at the limit. A kind of picture which we find in Renaissance art, medieval manuscripts, and we know in texts from antiquity. And here would have been a kind of a mechanized picture of it, something like this, perhaps, which is where I'm going to stop. I see I've run through my hour. I apologize. I did warn anyone who was on early that it's hard for me to be speedy with these topics, but I did my best. So thank you.